So think of each of these arrows as solar radiation, as an individual sun ray, so to speak. And so each of these, like I've said before, is a constant. However, on Earth's surface, it varies. And we can see that represented here with these arrows in the teal lines, those blue lines representing Earth's surface. And so you can go ahead and see which one of these is the subsolar point. And you should select this one right here. And so the subsolar point is the most direct. It is at a 90-degree angle or perpendicular to the surface. And I want you to go ahead and also look at the other arrows and the other angles and kind of their characteristics related to the red one. So if you go back and look at the previous slide, you'll notice that the arrows and Earth's surface, they vary as far as their position relative to each other. And so one of them, the subsolar point, the red one, has what we see at the top, that 90-degree angle, perpendicular. And so that's going to be where we find the highest energy is in those direct 90-degree angles, where it's the highest number, highest angle, closest to 90. Whereas the closest we are to 0, as we move down to the bottom, lower angle, we're going to have lower energy. So like I said before, incoming solar radiation, it's constant. The key to understanding variation is Earth's curvature. So here we have a high angle and a low angle to kind of emphasize what I've said on a previous slide. So a high angle, low angle. Both of these are the same width. However, if we look on the Earth's surface, we see the lower angle, it's more spread out. It takes up more space there on the Earth's surface on the green line, whereas the higher angle, much more concentrated. But both of them are the same. Both of them are the same width. And so we can see how the lower angle covers more surface area than the higher angle.
Now I'm going to use a flashlight to illustrate lower energy, higher energy using different angles. And so right now this flashlight, I'm not going to push any buttons to cause it to be brighter or to cause it to go dim. So I'm keeping it the same regarding the amount of solar energy I am sending to this nickel. The difference is as I go to a lower angle from 90 closer to 0, a lower angle, what you notice is the same amount of light is spread out over a greater area, but also at the same time becomes dimmer. So as we go to a lower angle, we can see it's quite dim, spread out, whereas if I go to a higher angle directly above, it's much more concentrated and focused directly on that bright shiny nickel.
Now, translating these flashlight examples to Earth's surface, once again we go back to what we've talked about beforehand. 2.5 times more insolation on average in the tropics compared to the poles. And that makes sense now that we understand that's related to sun angle. It's related to where the subsolar point is compared to where you're located. And of course, places along the equator are going to have more of that direct solar radiation, that 90-degree angle, compared to places further closer to where we are in the what they call the mid-latitudes, 40 degrees north to eventually up to the poleward areas, where obviously they get a much lower angle. And so it's not so much related, like I've said in 1.1, it's not related to how close we are to the sun. Instead, it's related to where we are in respect to the subsolar point, has a key role as far as understanding solar energy at Earth's surface.